Mass spectra can provide structural clues from the fragments observed and particularly from isotopic patterns. In the current era, where we rely on high-resolution mass spectrometry with soft ionization methods, you may never need to interpret an electron impact ionization mass spectrum. But you will see some fragments even in high-resolution mass spectra of structurally complex compounds. So it's worth briefly reviewing this. First of all, in mass spectrometry, only charged species will be detected. The ionization method forms a molecular ion, which is detected in this case at 121 mass over charge. The first fragment is M-16, which corresponds to the loss of NH2 radical to give an acylium ion at mass over charge 105. The loss of 16 is invisible because it is a neutral radical. Only the cation is observed. The acylium cation can further decarbonylate to lose carbon monoxide, a loss of 28 atomic mass units, to give the benzene cation, mass over charge of 77. We typically are not required to analyze to the left of the base peak, and I will not require that in this class. Hydrocarbon fragmentation gives the more stable carbocation, which is detected with loss of the more stable radical. For a linear hydrocarbon such as hexadecane, the methyl radical is less stable than the ethyl radical. Therefore, after the molecular ion peak, the first fragment observed is loss of ethyl radical to give a 14-carbon primary carbocation as a very tiny peak in the spectrum. For the branched hydrocarbon, we now see M-15 with loss of the methyl radical because the carbocation for mass over charge 211 is now secondary. Other secondary carbocations form from M-57, loss of a butyl radical, and M-141, which is loss of a 10-carbon radical. For saturated alcohols, the molecular ion is difficult to observe, as the predominant fragmentation patterns are loss of hydrogen radical from the carbon attached to oxygen and carbon-carbon bond cleavage, in the case of 1-pentanol losing a butyl radical to give a protonated formaldehyde at mass over charge 31. The secondary alcohol tends to fragment carbon-carbon bonds with loss of methyl radical in one direction and propyl radical in the other direction. As the propyl radical is more stable than the methyl radical, the pathway leading to the base peak at mass over charge of 45 is favored over the pathway that gives the fragment at mass over charge 73. For the tertiary alcohol, loss of the methyl groups gives mass over charge at 73. Loss of an ethyl group, M minus 29, gives rise to the base peak. For the diaryl ketone with one chlorine, the molecular ion has the distinctive pattern of chlorine 35 and chlorine 37, as well as a small contribution from carbon 13 in the molecular ion peak. I'm unable to interpret the peak at mass over charge of 181, but cleavage of the carbonyl group can proceed in either direction to give the acylium ion at 139, which contains chlorine 35 and 37, and the acylium ion at 105, which does not contain a halogen. The acylium ions, in turn, can decompose by losing a carbonyl to mass over charge of 111 and mass over charge at 77. Carbonyl compounds will also fragment by what is known as the McLafferty rearrangement. This is notable for converting an even mass over charge molecular ion into an even fragment structure by the following mechanism. The molecular ion in a gauche conformation undergoes what is shown as a radical process to generate a radical cation and a stable alkene. Only the radical cation is detected by mass spectrometry, in this case at mass over charge of 74. The alkene byproduct is invisible, corresponding to M minus 84 in the case of 1-hexene. I'll work a couple of problems to show how we can identify some substructures. For this problem, from the exact mass data, a molecular formula of C6H12O is determined. If necessary, review the index of hydrogen deficiency on page 15, which I tend to call the unsaturation number, UN, in this case equal to 1, consistent with either a pi bond or a ring. In the mass spectrum, we can see the loss of methyl group, M minus 15, and M minus 29 for the loss of an ethyl group. The even-numbered fragment at mass over charge of 58 is evidence for a McLafferty rearrangement. Finally, we also see loss of propyl groups at 57 and loss of a butyl group at M over Z of 43, which is the base peak. The mass spectrum provides considerable structural information, but I do not believe that we can make a claim for only one structure. The McLafferty rearrangement, along with a single oxygen and an unsaturation number of 1, suggests that this compound is either a ketone or an aldehyde. The peak at mass over charge of 58 is consistent with the McLafferty radical cation product that has a methyl group attached, although we cannot say definitively at which carbon the methyl group is attached. Likewise, there's one more carbon to account for, which must be attached to one of the two remaining carbons that is lost in the McLafferty rearrangement. But we cannot say with confidence which carbon that methyl group is attached to. Therefore, mass spectrometry must be accompanied by additional data such as infrared spectroscopy or NMR spectroscopy data in order to determine exactly which isomer of C6H12O is responsible for this mass spectrum. I've already covered how isotopes of chlorine and bromine give a distinctive pattern that reveals the presence of those elements. Since carbon-13 has a 1.1% natural abundance, and organic compounds tend to contain a large number of carbons, this 1.1% natural abundance of carbon-13 builds up quickly and gives a sense of the number of carbons. For example, with cyclohexane, the molecular ion peak of mass over charge of 84 is accompanied by a small peak at mass over charge of 85. And for a 6-carbon compound, note that the amplitude of the peak at 85 is about 6.6% of the amplitude of the peak at mass over charge of 84. I recommend looking for this in order to confirm a molecular formula.